All right, back with the next page. Next problem. Suppose that thing decays by natural radioactivity into two stages, or in two stages to that thing. Two stages would most likely be. So if I look at that, boom. Let's just start with the first one. So I've got the nucleus, the protons, boom. Let's go to there to something to A minus 4, Z minus 1, Y. So if I want those, let's take the first one. Electron plus antineutrino, and then alpha. So that's going to be A minus 0 and Z plus 1 because it's a neutron decaying into a proton. So I got that, and then alpha is a helium nuclei essentially, so it's going to be minus 4 on that. Since I'm losing 2 protons, 2 neutrons, that's going to be minus 2 there. So if I plug those in, step 1 is going to be A Z X. It's going to go and it's going to lose 0 up top, so that nucleus is going to stay the same, but it's going to gain 1. And boom, we have that. Then step 2 is going to be, so I have A, Z plus 1. Boom, it's going to go to A minus 4, and then Z minus 1. What am I thinking? Brain couldn't math for a second. And I'll just write it up. So if I'm looking for that, it looks like we have our answer as A. All right. Next problem. Let's see. All right. So it looks like this one has to do with Schrodinger's equation. So the wave function psi x is A e to the minus b squared x squared over 2, where a and b are real constants, is a normalized eigenfunction of the Schrodinger equation for a particle of mass m and energy E in a one-dimensional potential Vx such that Vx equals 0 at x of 0. Which of the following is correct? So it's looking to solve for V or A. So let's write down Schrodinger. We got E psi x equals minus h bar squared to m del squared psi x plus Vx psi x. All right, and psi of x is that equation a e to the minus b squared x squared over 2. So I need the second derivative of that. So I have psi prime is minus b squared x. The 2's will cancel. Ax b squared x squared over 2. Or writing it simply minus b squared x psi x. Then I need the second derivative, which is going to give me positive b to the 4th x squared, also just by psi. So taking that, we do a little bit of erasing. So I've got the second derivative of psi and psi. So let's just write this up here. Psi double prime is 4 squared. All right. Now I have to plug that into the Schrodinger. So I have E. I'm going to leave it just as what's supposed to be a psi. Psi x equals minus h bar squared to m. B for x psi x plus Vx psi x. I can pull out the psi x, divide them out. So I'm left with E equals minus h bar squared to m b to the fourth x squared plus Vx. Now plugging in our initial conditions, Vx, there we go. Vx equals 0 at x equals 0. I have E equals minus h bar squared to m b to the fourth 0 squared plus 0. Boom, that's all going to cancel to 0, giving me that the energy is equal to 0. We can eliminate those. Now we have that condition that the energy is equal to 0. I can go back, plug that into essentially this equation here, and get that h bar squared to m b to the fourth x squared is equal to the potential. Looking at those, just move it around so it's the same format. H bar squared b to the fourth x squared over 2m equals v of x, and that matches with B as our answer. All right. So it took one a little bit of writing, but it gives you fairly everything. As long as you know the process and are familiar with Schrodinger, it's not too bad. Next question. The energy levels of a hydrogen atom are given in terms of the principal quantum number n and a positive constant a by the expression. So this is just asking for the energy levels of a hydrogen. You know it or you don't. Energy levels of a hydrogen. I don't know why. Stop telling me how to do my job. And I'm going to get this one day. Boom, there we go. Equal to minus 13.6 EV over n squared. If we look at that, all we have to do is say that A is the minus 13.6. So now they have minus A over n squared. That is E. That one's nice and short and sweet if you know the equation. If not, good luck. Next one. Positive kaon has a rest mass of that number, whereas a proton has a rest mass of that number. If the kaon has a total energy that is equal to the proton's rest energy, the speed of the kaon is most likely. So I have that the rest mass of the proton is equal to 938, and the rest mass of the kaon is equal to 494. You're going to use E squared total is equal to rest mass or rest energy squared plus momentum c squared, where momentum is gamma mv. So if I want that the total energy of the kaon is equal to the rest mass of the proton, I could just plug that in and have that the rest mass of the proton squared is equal to rest mass of the kaon squared plus gamma mv of the kaon c squared. Then basically you're going to plug and chug and solve for v, where I have m proton squared c to the fourth equals m kaon squared c to the fourth plus gamma squared m kaon squared v squared c squared. I can cancel out quite a few c's, so if I pull a c to the fourth mk out, I'll be able to cancel that, that will go over. So I'll end up with mass of the proton over mass of the kaon squared equals 1 plus gamma squared v squared c to the minus 2. And I'm actually going to rewrite that as over c squared. From there, we want to see that the mass of the proton is about 4 times the mass of the kaon, so squared, that gives us 3, no, I'm sorry, 4. Wait. No, it's twice as much. I'm jumping ahead. Now it's 4 equals 1 plus gamma squared is going to be 1 minus v squared over c squared. All that under v squared over c squared. Do a little bit of, not scribbling, we're going to do a little bit of erasing. And let's go all the way up to here. So I'll leave that at the very bottom. Bring the 1 to the other side. I have 3 equals v squared over c squared, 1 minus v squared over c squared. Multiply that across. You're going to get 3 minus 3v squared over c squared equals v squared over c squared. 3 equals 4v squared c squared, 3 over 4. V squared c squared. And I'm going to have to erase this. There we go. I like writing every step out. It just helps me process through the problem. Then I have the square root of 3/4 equals v over c, which is about... yes, I know how all this stuff works. I don't know why it does that. It's like, oh, did you know you could do that? Yeah. Yep. 3 over 2, which is about 1.7-ish over 2, a little over 1.7, so about 0.86. And that's going to be 0.86c, which is about that answer. So looks like we got a pretty good answer there. I bet it's going to tell me, did you know if you press it again, you get more options? I don't know why it does that. All right. And on to the next question. 2 observers, O and O prime, observe 2 events, A and B. The observers have a constant relative speed of 0.8 c in units such that the speed of light is 1. Observer O obtained the following coordinates. 3, 3, 3, 3. Event B, 5, 3, 1, 5. What is the space-time interval between? So the space-time interval, delta S squared, is delta R squared minus delta T squared, where delta R is delta X squared plus delta Y squared plus delta Z squared minus delta T squared. This is another one of those, do you know the equation? But it's kind of an easy equation to kind of get stuck with. So from there, delta S squared is 5 minus 3 squared plus 3 minus 3 squared plus 5 minus 3 squared minus 5 minus 3 squared. Delta S equals 4 plus 0 plus 4 minus 4. Drop those out. And then I get delta S is equal to 2, which is answer C. All right. And going on to the next problem. Next problem. Which of the following statements most accurately describes how an electromagnetic field behaves under a Lorentz transformation? So the equations for that are in the X, the new field in the X direction is just that. The field in the Y is gamma, the Lorentz factor, times that minus the perpendicular magnetic field, and the field there is gamma EZ plus the field contribution there. The magnetic field in the X is also just that. The magnetic field in the Y is gamma By plus EZV squared C squared, and BZ equals gamma BZ minus EYV over C squared. So looking at those equations, we can see that it will not completely transform because we still have that aspect there. If there is initially only an electric field, after the transformation, there may be both electric and magnetic. That one checks out right now. I'm going to put a little check on it. Electric field is unaltered. That is incorrect. Magnetic field is also altered. It cannot be determined unless a gauge transformation is also specified. That is incorrect. We can see that B, if there is initially an electric field, it may have both. So we get our answer. And there we go. Next, which of the following statements concerning the electrical conductivities at room temperature of a pure copper sample and a pure silicon sample is not true? So let's look at that. We have copper, which is a metal. A couple things we know about that. The resistivity is proportional to temperature. And just quick as resistivity goes up, conductivity goes down. It has high conductivity. The impurities will raise resistance. Then we have silicon, which is a semiconductor, which, a couple things we know about that. The resistivity is proportional to the inverse's temperature. It has a lower conductivity, and impurities will lower resistivity. So going through that list, we're looking for the one which is not true. The conductivity of the copper sample is many orders of magnitude greater than that of the silicon sample. That checks out. Simply metals have a higher conductivity than semiconductors. If the temperature of the copper sample is increased, the conductivity will decrease. So as temperature goes up, conductivity decreases. That is also true since we see that the temperature goes up, the resistivity goes up, the conductivity goes down. If the temperature of the silicon sample is increased, the conductivity will increase. So we see that as well. The resistivity is inversely proportional to temperature. As resistivity increases, conductivity, as resistivity decreases, conductivity will increase. In addition, the addition of an impurity in the copper sample will decrease its conductivity. Yes, because it will increase the resistivity. That kind of leaves a process of elimination, but let's talk about it. The addition of an impurity in the silicon sample will always decrease its conductivity. That is incorrect because the resistivity goes down, which increases the increases the conductivity, giving us our example or giving us our answer of E. There you go. Words, it's tough.